Assalamu alaikum, dear students. We're back with another video lesson. In today's video lesson, we're going to start with the second section of chapter 2. Remember, this section is about rotation and inertia, which I can tell you that it is one of the main concepts in chapter 2. Now, if you're ready, let's begin. So the first thing that we have, we're going to talk about the center of mass. What is the center of mass? We can say simply the center of mass, that is the point where all the mass of the object can be considered to act when analyzing translational motion. And what does exactly that supposed to mean? Now, when we're, for example, let's say when we have an object, let's say, there is always a point where you can balance the object, where there is a point where it seems as if all the mass of the object is located at that point, and that is what is called center of mass. Let me give you an example. Now, we have this ruler, let's say. This ruler is 20 centimeter, let's say. If I place, let's say, my fingertip right at the center, for example, you can see that this ruler will be balanced at this point. Why will it be balanced? Of course, because there is a torque that is clockwise, there is a torque that is counterclockwise. These two will kind of like cancel the effect of one another, so the ruler will be balanced. But that is not the point here. Why will it be balanced right at the center? That is, or when it balances at the center, it feels like, or we can consider as if all the mass of this ruler is concentrated right at this point. That is what we mean by the center of mass of the object here. And of course, so we can also say that does that mean the other parts there, there is no mass at the other part? No, of course there are masses here, but this is the point where we say it can be considered. So that is not what it is in reality, because the mass is distributed over the shape, but we can, because it balances at this point, so we can consider as if the mass of all these rulers concentrated right at this point right here. Now, there are a few, let's say, study tips regarding this. At any point, if we have a uniform or a regular shape, the center of mass will always be right at the center. Okay, so remember this. There are two types of objects. We have regular shapes and we have irregular shapes, okay? So let me just perhaps write it down as a note for you here. So when it comes to objects here, we have two types of objects, okay? One of them, you could say there is regular objects, and then there is irregular objects. Irregular. Now, when it comes to center of mass for a regular object, the center of mass is always at the center. Remember this. What if it is an irregular object? We can say the center of mass is always closer to the heavier side. We can say it is closer. It is closer to the heavier side. To the heavier side. Now, remember this. Okay, now let's demonstrate a simple experiment here. This ruler clearly, it is a regular object or uniform object. What do we mean by regular? That means it can always be cut in half into equal pieces or symmetric pieces, you could say. So because this is a regular object, a uniform object, the center of mass is right at the center. But what happens if we have an irregular object? Let's say if I add a piece of, for example, eraser or another mass to one end of the ruler, now it is no longer a uniform object. Why? Because the mass of this side here, it is going to be, the mass of this side is going to be larger than the mass of the other side here. So now at this point it is irregular, don't forget. Well, if it is irregular, what happened to the center of mass? Will it still be located at the center? No, it is always closer to the heavier side. So let's see exactly where will it be balanced. Now watch this one. So if I place my fingertip here, all right, you can see that the ruler is going to be balanced. If you remember previously, my fingertip was just right at the center. But now you can see that the length of this side, it is more than the length of the other side. So now, of course, this proves what we just said. For a regular object, remember the mass or the center of mass will always be at the center, but if it is irregular, it is always closer to the heavier side. And that is the same thing for swing as well. You and your friend, let's say both are on a swing. If you want to, for example, have fun, let's say the support, let's say, must be closer to the person that is heavier compared to the other one here. So in other words, we could say if you cannot move the support, the heavier person must sit a bit closer to the center of mass so that you can enjoy having fun on the seesaw here. Okay, now let's get back to this one. When it comes to objects or center of mass, there is a regular object, there are irregular. If it is regular, the center of mass will always be at the center. If it is irregular, then it will be closer to the heavier side. Okay, now that is, of course, regarding these study tips. There's more. That is basically for the first and the second study tip. We have something else that is called center of gravity. What is the center of gravity? Now, we know that mass, or whenever an object has a mass, let's say gravity pulls on the object, right? Because that is where Fg comes from, you could say, that is the gravitational force which pulls an object down, or you can say the weight of a person. That is the gravitational pull on a person. Whenever there is a mass, there's a gravitational pull on the object. But remember one thing. Whenever we have a regular object, let's say, we said if the center of mass seems or can be considered to act at this point, isn't it the same as all the mass of the object is concentrated, located at this point right here? Yes. If that is the case, we know that gravity always pulls on mass. So based on this, we can say wherever the center of mass is, that is where the gravity pulls, all right? And that is what we call center of gravity. By the way, in a lot of books, there's no difference between center of mass and center of gravity. And of course, our book does not differentiate between the two, because you could use this two interchangeably at this point right here. Okay, now for many situations, like we said, center of mass and center of gravity are equivalent here. Now this concept here, these few lines, I would like to skip them for now and come back to this in a second. But first of all, let's define center of gravity. We said center of gravity is the point where an object's mass is considered to act, and that is where let's say, located, right, or concentrated. We said center of gravity, that is the point where gravity acts on. So if the mass is concentrated at this location, of course, that is where the gravitational force will act on that point there. Now, we have a section review question. We have some examples. The question says, describe the approximate location of the center of mass of the following objects here. Now, the first object that we have is a meter stick. And whenever you hear a word meter stick, and I need you to write a note for yourself. Whenever it says a meter stick, that means this stick, it is 1 meter. Because later on, we could have a meter, for example, rod, a meter support. So whenever you hear meter something, its length is 1 meter. Okay, so where do you think the center of mass of a meter stick is? Clearly, meter stick is a uniform or a regular object, which is going to be right at the center. If we assume that this is the 0 mark and this is the 100, let's say, mark, so clearly the center of this meter stick is going to be right at the 50 centimeter mark, or you can say 0.5 meter mark, and that's it. So it is right at the center. What about the second shape or object that we have? It is a bowling ball. Now for the bowling ball, you have to pay attention a little. Now if bowling ball was a perfect sphere, the center of mass would be right at the center. Wouldn't that be? Because we just said that when we have regular objects, the center of mass would be right at the center. But look, for bowling ball, there are gripping holes, right? That is basically the holes where you hold the bowling ball, let's say. So at this point here, can I say the mass of this side here, it is going to be less compared to the mass of this side? Yes. And if you remember, we said, now, is this bowling ball regular object now? No, it is irregular. And we said if the shape is irregular, the center of mass will always be closer to the heavier side. Now, because this side is heavier, we'll say center of mass that is close to the center, but a bit away or a bit further away from the gripping holes, or these holes you could see here. So it is going to be slightly to the side that is heavier. Okay, now the next objects that we have, it says an ice cube. Whenever it says a cube, whether if it is an ice cube or whatever, the center of mass will always be right at the center. So we can say it is at geometric center. That's it, Annie. What about a donut? It is also a uniform, you can say a regular shape, so that is also going to be right at the center of the donut here, right? We don't care if it is empty or whatever, so we're just saying right at the center, which is going to be right at this point here. Okay, now what about a banana? This one is a bit different here, and there's only one example where concerns this one here, because is the shape regular? It is not, it is irregular. So what do you think you'll do at this point here? You'll have to cut it in pieces where you can get equal pieces at this point here. So, by the way, let's just make it simple. If this question ever came, you could say it is in the middle along the inside. What exactly do we mean by this? Now, if, let's say this is a banana. If I make a circle here, complete circle, this is the outside of the curvature, you could say, or the curve here. This is the inside here. So we'll say it is along, or you can say in the middle. That is exactly where you could say it is, but along the inside here, or closer to the center of the inside. That is where it is. And if you cut it in the, for example, in this part here, you sort of kind of like get equal pieces. Let's say considering all these parts here and there, hopefully you'll get the same piece. For this one, it's really difficult to get the exact location of center of mass. This is why the question says, give an approximate location of each of the following here. So you don't have to be that precise. Just remember, if banana question came, you could say in the middle along the inside. If not, you could also say it is towards the center of a banana, which is there, depending on its shape and curvature, because of course, once you go to the store, you'll see that these are not, all of them are in one shape and size. Okay, that is regarding the center of mass of different objects here. Now, remember this, I would like to start with this one, then go back to the points that we just left here. That is more about combination of rotational and translational motion. In other words, for example, if you have a stick, let's say, or a thin rod, let's say, what happens if you throw this one in the air? Okay, well, two things would, or you can say something interesting would happen. Let me tell you very easily regarding this one here. Let's say there is a stick, okay, and here's a stick. This is the center of mass of the stick. Clearly, it is a uniform shape. Now, what happens here, let me name these two ends of a stick. This end is A and this end is B. Once we're throwing this stick into the air, remember this. Now, these two ends are going to rotate about the center, but the center itself, it is going to follow a parabolic path. What do we mean by this? Now watch this. So if we're going to throw this one, right, into the air, let's say, so you can see that the center of this object, it is going to follow a parabolic path, but the two ends are going to rotate about the center here. So let's copy more. That's what happens next. This is going to be even more, we could say. Let's make one more copy. Right down, you could say this is how it is going to rotate. Now, do you see the pattern, what happens here? Right? You can see that these two ends, right, are going to rotate about the center of mass here. The two ends are rotating about the center of mass. The two ends, you can see this is how they are rotating. Okay, this one too, about the center. But the center of mass, it is moving in this curved path, which is in physics is called parabolic path. Now at this point, of course, we could say, let's just summarize this tree here. Now, whenever it comes to a stick, we could just say the motion of the two ends, or we could just summarize this one here. Let's say the two ends, let's just make it shorter here. Two ends, right? And we could say the center. We're talking about the motion of, by the way, the two ends, and the motion of it is center. So the two ends will rotate about the center. And I need you to take a note for this, about the center. Because it is rotation, so we can say this is a rotational motion. Rotational motion. What about the motion of the center? As you can see that because it is moving in a parabolic path, so we could just say the motion of the center would follow a parabolic path. Parabolic path. And of course, if we treat this one as a point mass, that'll be translational motion. Okay, so we can say, or in order to study the motion of the center, we can, in that case, of course, we'll consider the center of mass as a point mass, then it would follow a parabolic path, and that is for translational motion. But the two ends are going to rotate about the center. Of course, they will be rotating. Now remember, at any point, if you're asked about a meter stick thrown or being thrown in the air, the two ends will always rotate about the center, but then the center will follow a parabolic path. Remember, that is if it is thrown. If it is dropped, that's a different case. Don't forget that. All right, so let's go back to what we have, and we have this example too. You can see that this guy is throwing a stick. These are the two ends here, and A and B. You can see that these are rotating about the center, but the center itself, it is following a parabolic path. Make sure you wrote the note. If not, you can read this one. Of course, it tells you exactly what we just said. Now let's go back to the part where we left, and that is this part. Right? It says combining rotational and translational motion. This diagram you see, this is not a backbone. This is a hammer that is thrown in the air. And if I draw the hammer here, because it is irregular shape, the center of mass is going to be somewhere, we could say, close to this point right here. So now these two ends are going to rotate about the center of mass. Well, the center of mass that is going to, we could say, follow a parabolic path, and this is what you see. So says the hammer in the figure to the right rotates about at the center of mass as it moves through the air. Watch this. We said, remember, the center of mass is basically follows a parabolic path, but both ends, or let's say the ends of a hammer, spin or rotate about the center of mass, and this is the note you just wrote. Okay, let's continue with the next thing. The next thing is we have something called moment of inertia. And remember this is one of the main concepts that we have in chapter 2. If you master this, that means you almost like mastered chapter 2. If not, keep revising until you master the concept. What is exactly moment of inertia? Of course, in order to help you with this, I'll have to take you back to grade 11 for a second, and then after that, we'll talk about moment of inertia. So remember, in grade 11, it's too much, let's zoom out a little bit. In grade 11, remember this. Okay. We said, watch this, we have two objects, let's say. One of them has a mass of 10 kilogram. The other one has a mass of, let's just say, 25 kilograms. If we apply a force of 100 Newton on both of them, now, 100 Newtons. If I ask you a question like, which one is easier to move? Of course, you would say the 10 kilogram, right? Because the bigger the mass, the more difficult to move. Can I also say the bigger the mass, the more resistance to move the object? Yes, and that is what is called inertia. That is what we had as inertia in grade 11. So we can say inertia, remember, inertia, it is the resistance, let's say, or the tendency to resist translational motion. Translational motion. If I give you a proper definition, maybe something better, we can say inertia, it is the tendency of an object to resist, to resist the change in its motion here. In other words, we can say if the object is not moving at rest, it wants to keep, staying at rest. If it is moving, it wants to keep moving, like it doesn't want to stop, right? So whatever the state of the motion of the object is, it wants to keep that. It doesn't want to change. That is what is called inertia. And of course, what determines that? We can say mass determines that, because can I say the bigger the mass, the more the difficulty? Yes, and this is exactly, we can at this point here, we could say inertia is determined by the mass of the object, or mass determines the inertia. In other words, how easy or difficult it is to move an object or to stop an object, it is related or depends on the mass of the object. But that is all grade 11 when an object is moving in a straight line. Do we have resistance for objects that, because we're dealing with rotational motion this year, Do we have resistance for objects that trying to rotate? The answer is yes. And that resistance to rotational motion, we don't call it inertia, we call it moment of inertia. What do we call it? Moment of inertia. And its symbol is letter I, or capital I, right? Moment of inertia. And we have an equation for that. What is the equation for moment of inertia? We'll say I, it is equal to a factor, a constant, a number, times mass of the object times the radius of the object. And you can clearly see that moment of inertia here, it is measured in the unit for mass. You can see that it is kilogram. The unit for the radius, it is meter. Because of this squared, we can say meter squared. So now the unit for moment of inertia, it is kilogram meter squared. But once again, how do we define moment of inertia? We'll say it is the tendency of an object that is rotating, let's say, to resist a change in its rotational motion. I'll repeat the definition. The tendency of an object that is rotating to resist a change in its rotational motion. In other words, whatever for example, the state of the motion of the object is, it wants to keep or stay at that state, let's say. If it is at rest, it wants to stay at rest. If it is rotating, it wants to keep rotating, not to stop. That is basically what is called moment of inertia. So that is moment of inertia. It is, in simple words, you can say it is a resistance in rotational motion here. Okay, now moment of inertia, we said it is measured in kilogram meter squared. Moment of inertia here, it is a scalar quantity. What do we mean by scalar quantity? Right? When we say scalar quantity, that means it has no direction, right? And if it has no direction, that means, of course, it cannot be negative, right? And if there is anything that is rotating, clearly they have some mass. And if they have some mass, there will always be some resistance to rotational motion. So in other words, they can never be negative or zero as well. So they have a value which is always bigger than zero. As long as there is a mass, there's an object that is rotating or trying to rotate, and then they will never be negative because they are a scalar quantity. Now, there is one more thing regarding this. Different shapes show or provide different resistance to, let's say, rotational motion. Now, let's talk about what are the moment of inertia for different shapes of, let's say, or for different objects, let's say. So once again, we said moment of inertia, it is equal to a factor, a constant, you can say a number, times mass times radius squared. That is moment of inertia. But of course, we have different, let's say, numbers or different resistance to different shapes. And now we're going to talk about each one of them. Now, the first shape that we're going to start with, you could say a point mass, or you could say a thin hoop here. So the first equation for moment of inertia, we can say it is 1 times mass times the radius squared in here. So that is clearly 1, you could say. Okay. Now, what do we use this equation for? We can use this, of course, for different shapes. One of them, you could say, these are some of the shapes that they have this. You could say a point mass, all right? Or you could say a thin hoop. Let me just write it perhaps below. A thin hoop. But this thin hoop, of course, it must be about, let's say, symmetric axis. Symmetric or symmetry axis, let's say. Let me rewrite it. Okay, about symmetry axis, and that is going to be through the center. Through the center. Or you could just say about the symmetric axis, and that's it. Through the center would be unnecessary at this point, about symmetric axis. Now, of course, what are other shapes, for example, that look like a point mass or a thin hoop, you could say, for a ring as well. Whenever it says any shape that looks like a ring, we can use this equation for. Or you could use, let's say, a hollow cylinder. hollow cylinder. These are, of course, some of the shapes that we'll use this one for. Okay, so point mass, thin hoop, about symmetric axis, you can say symmetry axis, a ring, let's say hollow cylinder. There's also, we could say, bicycle wheel as well. Bicycle wheel. Remember, if it is just a wheel, it is going to be different, but if it is bicycle wheel, doesn't it look like a ring shape? Yeah, so that is also same equation. So these are all the words, of course, that you can be asked regarding the first one here. Now, what about another shape that we have, let's say, and that is, we can say moment of inertia is equal to 1 over 2 this time, mass times radius squared. Mass times radius squared here. So now we can say, that is, for what shape are we going to use this one here? You could say for a disc, okay, for a coin, anything that looks like a disc, right? Coin. We can also say thin hoop again, but this time about the diameter. Don't forget about the diameter. Watch this. If it is thin hoop about the symmetry axis, it is going to be 1 times mass times radius squared. But if it is thin hoop about the diameter, it is going to be 1 over 2 mass times the radius squared. And what exactly is this, by the way? If I draw a shape here, that is a point mass that is moving, let's say, in a circle around this one here, or it could be anything, or a ring shape here. That is how, for example, the thing would look like here. That is the center if it is a point mass about the center here. What about a thin, or you could say a thin hoop about the symmetry axis? What if it is a thin hoop about the diameter? Now this thing here is just almost like, for example, you have this one is going to flip from side to side here instead of just moving in a circle at that point here. So that'll be thin hoop about the diameter, you could say. What other shapes we have? You could say, you could also say, for example, solid, you could say solid cylinder. See, we have hollow cylinder, looks like a ring, right? But this time here, we have solid cylinder that looks like a coin. Solid cylinder. Solid cylinder is another shape, of course, and sometimes you could say a pulley, or it could be a wheel as well. Remember, if it is a bicycle wheel, that is going to be 1. If it is a wheel, just like a wheel, like a pulley, for example, in that case, is going to be 1 over 2. But the question, of course, must clarify which one is it so that you don't make any mistakes at this point here. Now, that is the second equation, you can say. What about the third equation? Now, for the third equation, we have moment of inertia. It is equal to, right? It is equal to what? It is equal to 2 over 3 times mass, let's say, times the radius. Let me just write this one in black. 2 over 3 times mass times the radius squared. And what do we use this equation for? We'll use this for a thin spherical shell. For what? For thin spherical shell. So for thin spherical shell. And how does a thin spherical shell look like? It looks like a basketball. And a diagram would be this. There is a thin shell, but inside of this is going to be hollow here. Or you could say, like it's not filled with the same object or whatever. Let's just call it hollow. So this is the shell. And you can see that it is thin. So most of the mass, or all the mass, you can see that it is distributed at the edge around this one. But what is the difference between this and this one? This is a ring. Remember, this is a sphere, just like a basketball. So there is the shell, the whole thing. It is just the inside is hollow. If I draw, let's say, a diagram for this one here, for a disc or coin, this is how it looks like, right? This is basically the sad thing regarding this one. These are basically 2D, so that is the best that I can draw here. Now, another shape for, let's say, moment of inertia, let's say number 4, we can say moment of inertia for another shape is 2 over 5 mass times radius squared here. 2 over 5 times mass times the radius. And what is this, or what do we use this equation for? We'll use this one for solid spheres. Solid sphere. Like what? Like a bowling ball. Like what? Like a bowling ball. What is the difference between this and that? This one is inside is hollow, you could say, but bowling ball, you know that the inside is filled with the, let's say with the material, whatever that is made of here. So inside is not a hollow, so you can see that the mass is distributed around the axis of rotation at this point here. So these are the four main equations for moment of inertia that we have. There are two more left actually. So let's cover that too as well. Now this time we could say number 5, the moment of inertia for a thin rod or rod but about the center. So here's, let's say, the thin rod, which is basically perpendicular through the center. This is how it is going to rotate. So you could just say it's rotating about the center. Maybe these are not one of the best things, right? So these ends, you could say, are rotating about the center here. So we can say the moment of inertia for this one here, it is equal to 1 over, if it is, by the way, if it is at the center, we can say 1 over 12 times the mass, right? Times, if you remember in the previous examples where we're using radius here, the reason why radius is because the distance to, for example, from the center to the edge is a radius here for all of these shapes here. But at this point here, instead of the radius, we have the length of the rod in here. So instead of radius, we're going to call it the length. But these are always squared. Let's just see if I wrote square in all the other cases as well without. Yes, so these are always squared here. That is, we can say for a thin rod, okay, but if this thin rod, you can see that it is perpendicular through the thin rod, you can say about the center, or perpendicular, let's say, but this axis of rotation is right at the center. Or you can say the axis of rotation is passing through the center, right? So we can say thin rod, we could say about the center, okay? About the center. Now, what about the other one here? Let's say the last moment of inertia equation, by the way. Moment of inertia, it is equal to 1 over 3 times mass times the length squared. But when will it be the length squared? Now, this is the same rod, but this time, instead of passing through the center, it is the axis of rotation is clearly passing through the end. So again, thin rod, but this time you could say the axis of rotation is, or you could say rotating perpendicular, all right, through the end. Asha, rotating perpendicular through the end. Through the end. So remember, that'll be the difference between the two. One of them is through the end. That is the whole length here. And then the other one is perpendicular through the center of the rod here. So these are the equations. Even though we don't have any equation that we use these equations for, but of course there are questions. There were questions in Wazari that they can ask for one of these as well. And sometimes remember this, these are very easy, but of course they could change things here. And one of the quizzes that I had, I've just changed this number, for example, for a thin rod, let's say, that is perpendicular, let's say through, it is the center. I've just changed this number from 1 over 3, I made it, let's say 2 over 6, and a lot of them could not recognize this because they didn't see this one. But all you have to do is just like, isn't this, let's say if you simplify this, wouldn't you get 1 over 3 again? So these are exactly the same. So be careful with tricks like this, or of course you can use them in questions as well here. So remember, these are, we can say, all the equations for moment of inertia for all these shapes. Hopefully I didn't miss out any names. If not, of course, you can check out the table if there is any other names that I missed here. But these are the most keywords that you need them with their equations as well. So now let's see if you've summarized all the equations real quick. The first one we said, we have moment of inertia, it is 1 times mass times the radius squared. The second equation was, we could say, by the way, you might say, how do I memorize this? All you have to do is just write them on a paper, maybe 5 times, 10 times, 15 times, 20 times maximum. And of course, you will automatically memorize without doing much more efforts in here. So 1 times mass times the radius squared. Here, 1 over 2 mass times the radius squared. The third one was, we could say moment of inertia was 2 over 3 mass times radius squared. The fourth one was moment of inertia, we said 2 over 5. See, these are 2 over 3 and 2 over 5 mass times radius squared. And then the fifth one was moment of inertia. It was 1 over 12 mass times length squared. And then you could say the sixth one, it is moment of inertia 1 over 3 mass times the length squared here. Remember this is for a point mass, okay, point mass, or you can say for a ring or anything that looks like a ring, right? This will be the keyword. You could say for a ring or anything that looks like a ring here, or it makes a ring path shape, let's say. There's an object, let's say, that is rotating, right? If you didn't know whether if it is a ring or not, just, for example, see or imagine the shape of the path that it makes, whether if it looks like a ring, then you can always use this equation. What about this one? We said anything that looks like a disc. These are, just remember these main words here. Hopefully it makes it very easy to remember. All right, this one here, we said thin spherical shell. Thin spherical shell, like a basketball here, so that would be it, all right? And then for this one, that is for a solid sphere, like a bowling ball here, okay? These are, just remember the difference between the two. And this is thin rod, you could say, about the center. This is thin rod about the end here. And that would be all the equations. Hopefully you can memorize them way easier in this format without doing a lot of effort. Now there's one more thing, let me tell you this. Based on these equations, what does the moment of inertia for an object depends on? It depends on three things. Moment of inertia, it depends on, we could say, the mass of the object, right? The second, you could say the shape of the object, all right? And then the third thing, we could say the mass distribution around the center or the axis of rotation. The mass distribution. Okay, I hope the spell is correct here. So once again, moment of inertia, you can see that the equation, it is c times, I would rather to call this one here, factor constant here, which is basically for the shape, times mass times the radius squared. So you can see that it depends on the mass, which is directly proportional, okay? And also depends on, we could say, the radius, right? Which is, that is basically with the square, of course, you can see that. So if we double the mass and double the radius, which one of them has a bigger effect? That would be the radius, because it is squared. What if we decrease them? Of course, like half this and half that, of course, you can see that the effect of this one will be bigger because it is squared. Now, what about the shape? Of course, you can see that different shapes have different moment of inertia. And then what about mass distribution here? That is also very important. As you can see here, these are both spheres in here. But what is the difference? They have different equations for moment of inertia, because one of them, the mass is distributed at the edge, you could say, at the rim of the object here, but the other one is the mass distributed, let's say, kind of like evenly around the axis of rotation. So that is the effect of mass distribution on moment of inertia. And we can also say this. Have you noticed the fractions or these numbers here? 2 over 5, of course, you get 0.4, and if it is 2 over 3, that is 0.67 by rounding this one here. 2 over 3, that would be this. In other words, we can say this is something very important. The closer the mass or the mass distribution from the axis of rotation, the less the inertia. That is something you need to know, this one here. So once again, we can say the closer the mass from the axis of rotation, remember this, the less the moment of inertia. And later on, we're going to see, we just said that moment of inertia, it means the resistance to rotation, yes or no? Can I say the bigger the moment of inertia, the more resistance to rotate? Very good. What about if I say the less the moment of inertia, which means the less resistance to rotate? In other words, if the moment of inertia is small, right, then of course angular speed is going to be large. So we can say these two are inversely proportional, because the larger the moment of inertia, that means the more the resistance. And if the resistance is more rotational resistance, you can say. Rotational resistance. And if the resistance is large, then what happens to the angular speed, of course, is going to be smaller. So these two are, moment of inertia and angular speed are inversely proportional, and I need you to remember this. Later on, we have equations just to prove or demonstrate this, but for now, just remember moment of inertia and angular speed are inversely proportional. I hope these are all the equations or the important things you need to know at this point. I hope you understood them very well, Baba. All right, so here's the definition of moment of inertia. Remember, the keywords are all like written in bold here, just so that you can focus on these keywords. It is the tendency of a body rotating about a fixed axis to resist a change in its rotational motion. It is measured in kilogram meter squared. That is the first part. We said the equation that we use for moment of inertia, I, that is the symbol, that is equal to a fraction, a constant, times mass times radius squared. We can see that moment of inertia is directly proportional to each one of the two here, but the radius is squared, so it has a bigger effect in that case. These are the table that you need to know for the moment of inertia for all the shapes that we have in our book here. This is the first one. These two are basically, they have the same equation. That would be for a thin hoop about symmetric axis, or it could be a ring, bicycle wheel, or hollow cylinder, or it could even be a point mass about the axis. These are all the same thing here. And then the second shape that we have, these two also have the same equation. A thin hoop about the diameter, or you can say a coin, a pulley, or a solid cylinder. These all have the same equation. A disc cylinder about the symmetric axis too, you could say these are 1/2. So 1 times mass radius squared, 1 times mass radius squared, 1/2, 1/2. Now, if I jump, for example, make a jump here, so this is a solid sphere about the diameter. Remember this, a solid sphere, we said the equation is going to be 2/5 mass times radius squared. What about the thin, that would be like a bowling ball as an example. Thin spherical shell about diameter, or you could just say thin spherical shell is going to be like a basketball, which is going to be 2/3 at this point here. The last two shapes that we have, we said one of them is thin rod about perpendicular axis, but through the center. Whenever you see through the center, that is 1/12. But if you see the same thing, it says through the end, that is going to be 1/3 times mass times the length squared. And also remember this one. This is also something very important. Spinning was out a few times. Says, what is the rotational analog of mass in translational motion? We said, how much resistance an object showed to, let's say, to change its state of motion, the mass would determine that, and we call that inertia. So, but what do we have the substitute, the analog of inertia in rotational motion? We call it moment of inertia. So the analog of mass in translational motion, it is I, or moment of inertia in rotational motion. Oops. All right, now the next thing that we have is these study tips. These are also very important, which we also mentioned that as well. Moment of inertia is a scalar quantity, which means its values are neither negative nor zero. So they're always positive and they can never be zero here. Okay, now we also know that the further the mass of the object from the axis of rotation, the greater the moment of inertia. And that is, of course, we get this from the equation because moment of inertia and the radius are directly proportional. Moment of inertia, let's change the color here. Moment of inertia, it is directly proportional with the radius squared, which means that the further the mass from the axis of rotation, let's say here's the mass. What happens if you make the circle bigger here? Now the mass would go even further, of course. So the further the mass from the axis of rotation, the bigger the moment of inertia, which means more resistance, okay? And if the resistance is more, it would be more difficult to rotate the object. Now the last point, of course, is very important. I need you to remember this one. It says the relation between, or the relationship between the angular speed, omega, and moment of inertia, I, is inversely proportional, like we said. The bigger the moment of inertia, that means the more resistance, the more difficult to rotate, which in that case it is going to rotate very slowly. But if the moment of inertia is small, that means there is less resistance. If there's less resistance, the object can rotate way faster. Okay, now there's also a difference between inertia, that is grade 11, and moment of inertia, that is going to be this year here. Okay, so what is the difference between the two? I want to pay attention, especially to point number 2, because there was a question regarding this one. So this is grade 11, and this is, you could say, grade 12. Okay, so mass or inertia. We said it is the inertia that resists the change in translational. What about moment of inertia? It is a resistance in rotational motion, you could say, right? So it is the inertia that resists change in rotational motion. Okay, the next thing is, we know that the inertia depends on the object only, or the mass of the object, you can say. The heavier the object, the more difficult to move the object on a straight line, let's say. But this one here depends on 3 things. Depends on the object's mass, depends on the shape, and also depends on the mass distribution around the axis of rotation. There was a question we're saying the moment of inertia depends on what? The options were like depends on the mass, depends on the radius, depends on the mass distribution, or all of them. Of course, you had to choose all of them. But if it was just inertia, then it would have been the object or the mass only. All right, what about point number 3? Point number 3 says, mass is an intrinsic property of an object, doesn't change. What do we mean by this? When we say an intrinsic property, that means you can cut the object into so many pieces. The mass still remains the same. But will it be the same for moment of inertia? It is not an intrinsic property. Let me give you an example. Imagine we have a bowling ball that is made of metal. All right, now if it is made of metal, that would be a solid sphere. The equation for moment of inertia, if you know, by now it is equal to 2/5 mass times radius squared. Now imagine that we have a very strong, let's say, hydraulic press. Now what happens if we press this bowling ball? It might change into a very thick coin, let's say. So will the shape change from a bowling ball into something like a disc? Yes. But if that bowling ball changed to something like a disc, well, it is moment of inertia remains the same. No. Now, because the shape will change, even though the mass and the radius did not, so at that point, of course, we'll use the equation for a disk, which is 1/2 times mass times radius squared. See? From a bowling ball, from one equation changed to another. Now, that same thick coin, let's say, what if we use that hydraulic press again, but this time we're just kind of like pierce a hole through the center, right? Because we have a strong hydraulic press, we could just make a hole right in the center of that disc. And now make that hole bigger and bigger without changing, let's say, the shape on the radius. At this point, from a disc, from a coin, it looks more like a ring at this point. But here's my question. Will the moment of inertia or the equation for moment of inertia remains the same? The answer is no. We're going to use 1 times mass times radius squared. So you see, the same shape and mass, for example, change from a solid bowling ball to a coin, let's say a disc, and then after that to a ring shape. But of course we know that their moment of inertia is going to be different for different cases here, or in each cases. So this is what I mean by it is not an intrinsic property, because if the shape and the mass distribution change, the moment of inertia will change. Unlike for the mass, no matter how many pieces you cut the mass into, the mass will always remain the same. Okay, now for mass it is measured in kilogram, while for moment of inertia it is measured in kilogram meter squared. Now I think it is time to answer a few Zadi questions here. Remember the keywords. These keywords makes it very easy for you to answer them. The first one says, the tendency of a body that rotates about fixed axis to resist. To resist what? A rotational motion. That'd be moment of inertia, and that is this one here. What if they were changing, for example, what if the question was like to resist a change in translational speed? In that case, of course, it would have been inertia only, not moment of inertia, but we don't have that in the options here. So pay attention to the keywords so that you don't make any mistakes. Moment of inertia of an object depends on what? This is the question that I told you. The shape, the mass distribution around the axis, or all of these. It is all of this, right? Okay, now 3 says, which rotational quantity is the analog of mass in translational motion? So in translational motion, we have mass, which is the inertia. In a rotational motion, we have moment of inertia, don't forget. So it has to be moment of inertia. And that is option A. It is very important to memorize all these equations for moment of inertia for different shapes because you will need them for questions like this one here. Okay, so for example, it says moment of inertia for solid sphere. Remember solid sphere? We said it's like a bowling ball here. About or a round diameter can be found by what? Which one of these equations would it be correct? For solid sphere, we know that it is 2/5 mass times the radius squared. Remember, 2/3 would be for thin spherical shell, 1/2 would be for a disk, and mass times radius squared would be for a point mass, or you can say for a ring. Okay, question 5 says the moment of inertia for a regular object where m is the mass and r is the size of the object rotating around a fixed axis that passes through its center can never be larger than what? Okay, now I think this one is a very good question, and it is time for me to take you back to this one. Out of all these equations here, which one of them, or which one of these shapes would have the largest moment of inertia? All right, now once again, let me just change these, let's say numbers, all right, or fractions into numbers. Here's just one, that is 1. 1/2, that'll be, it's the same as 0.5. 2/3, we said it is the same as 0.67. 2/5, it is the same as 0.4. 1/12, all right, let me get a calculator for 1/12, which is going to be, it is 0.0 something. Let's see, what is it? 1/12, it is going to be 0.083. What about 1/3? That is clearly about 0.33, I guess. Yes. That is 0.333, you could say, and you can see that it extends this number here. So which one of these is the biggest moment of inertia? It is for this one here. Okay, so that'll be the, of course, now remember, let's go back to the other question here. It says moment of inertia, or the maximum, the biggest moment of inertia that you can have, it is 1 times mass times the radius squared here. Okay, so what will be the answer to this question now? It says, can never be larger than what? Can never be larger than? Can never be larger than this one. Why it can never be larger than this? Because that is for a point mass, where the mass can be at the maximum distance from the axis of rotation. Now we have another question. Says the student says that moment of inertia and mass are the same quantity. Explain what is wrong with this reasoning, or with their reasoning here. Can we say the mass and moment of inertia are the same thing? No, because mass is the resistance in translational motion, you could say. But moment of inertia, it is a resistance in rotational motion. That'll be the difference between the two. So these two are not the same thing. You could say resistance to change in translational. That'll be better to say. What is the relation between mass distribution and moment of inertia? We said earlier that, remember these diagrams here, right? So one of them, let's just say if I have a thin spherical shell, like a basketball and a bowling ball. Oh, these are, let's say, the same shape, same radius as well. But because one of them, you can see that the mass of this one is distributed closer to the axis of rotation, so the moment of inertia for this one is going to be 2/5 mass times radius squared. In other words, you can say it is 0.4 times mass times radius squared. But for this one, like a basketball, because the mass is far from the axis of rotation here, okay, so in this case, the moment of inertia would be larger, which is equal to 2/3 mass times radius squared. In other words, you can say 0.67 times mass times radius squared at this point here. So based on this, we can say the further the mass from the axis of rotation, the larger the moment of inertia. In other words, the more difficult it is to change it as rotational, or it's more difficult to change it as rotational motion here. And of course, the less the angular the speed here. Okay. So once again, it says the further the mass from the axis of rotation, the bigger the moment of inertia. All right, I, which is the smaller the angular speed, and vice versa, like a ring and a solid sphere. Now we have a very cool experiment actually. Says explain what happens when you let three objects like a solid sphere, a solid cylinder, and a cylinder to roll down along a ramp in the absence of friction. Imagine there is no friction. These objects are going to roll down, don't forget, okay? So now one of them is like a disk. So what is the moment of inertia for a disk? It is 1/2. You know that, right? And then the other one is a bowling ball or solid ball, you can see. So the equation for solid ball, it is 2/5. And you agree with me, right? That is mass times radius squared, mass times radius squared. And this one is like a whole cylinder, which is 1 times mass times radius squared. A lot of times we might not even write this one here. Now, if I convert this one to fractions or decimals here, this is 0.5. This is, let's just use a different color. This is 0.5. This is 0.4. And this is 1. Now, if I ask you here, and these are all of them, of course, have the same mass and radius, and all of them are start to roll down at the same height. So what it is different is these factors here. Based on these factors, which one of them is the smallest? It is 0.4. Which one of them is the largest? It is 1, you can say for this one. But remember, earlier we said that moment of inertia, it is inversely proportional with angular speed. In other words, if moment of inertia for an object is large, then angular speed for that object is going to be very small, or smaller, let's say. But if moment of inertia for an object is small, that means there is less resistance, then the object is going to roll or rotate faster, so angular speed is going to be larger here. So based on these three shapes here, which one of these objects do you expect to reach the bottom of the incline first? That is going to be the solid ball. Why? Because it is moment of inertia is the least. So if it is moment of inertia is the least, that means there is the least resistance to a change in its rotational speed, which means that it can travel the fastest. If moment of inertia is the least here, it can travel the fastest. So this one is going to be the first to reach to the bottom of the incline. This one is going to be the second, right? Then this one is going to be the last, or you can say the third one for this one here. Why? Because it is moment of inertia is the most, so angular speed would be the least for this one. This is why this one would reach the last. This will be the first, and that is the last. And here's the explanation. Now here's another question here. It says, why is moment of inertia greater in a hollow cylinder than in a solid sphere? Right? I hope that is also a very good question. There is a hollow cylinder, and then there is a solid sphere. Here's a hollow cylinder. Looks like a ring, right? You can see that all the mass is distributed far from the center. But if it is a solid sphere, you can see that the mass is distributed around the center, the axis of rotation here. So, and we also said that the closer the mass from the axis of rotation, the less the moment of inertia, right? And if that is the case, it can rotate way easier here. So the answer, or to answer this question, we'll say the mass of the hollow cylinder, it is concentrated mostly at the circumference, where you can say the mass is concentrated far from the axis of rotation, where the mass of the solid cylinder, it is concentrated, you can say on average, closer to the axis, which makes the moment of inertia to be less. All right. Watch this. Let's answer this question maybe, or this too, and then perhaps we'll end with this. It says, if both mass and distance from the axis of rotation are double, which one of them would have a bigger effect? Clearly, that would be the radius. We've mentioned that because moment of inertia is equal to a factor, you could say a constant times mass times the radius. So if you double the mass and double the radius, what do you think will happen? If you double the mass, the moment of inertia would be doubled, yes? Because these two are directly proportional. So if you double the mass, this will be doubled. But what if you double the radius, right? So here's moment of inertia. That is directly proportional with the radius squared. So if you double the radius, because it is squared, so the moment of inertia increases by factor of 4. So clearly, the radius has a bigger effect. And what do we use this, this note, or what is the use of this? You'll see the effect of this one right here. Now it says, 2 children are rolling down an automobile tire, rolling down a hill. One of them one of the childs, let's say, claims that the tire will roll faster if one of them curls up inside the tire. And then the other child says or claims that this will cause the tire to roll more slowly. Now, which one of them or which child is correct? Now, I need you to watch this one carefully here, but remember this diagram. Maybe we don't have to go to the other side. I'll just bring this one or the whiteboard here. Okay, watch this. So this is what we have at this point. Okay, so here's the tire. Let's use this shape maybe. Here's a tire. In both cases, let's say. Right, you can see that this tire, most of the mass, you can see that it is concentrated at the circumference here. So if that is the case, let's just say, what equation do we use to find the moment of inertia for this one? That is going to be 1 times mass times radius squared, because that looks like a ring, you could say. Most of the mass is concentrated at the circumference, which is far from the center. But what happens if one of the child is going to curl up inside the tire here? Let's say this is the same tire now, but imagine this is one of the child that is going to curl up inside. Not very good at drawing here, but let's say this is one of the childs here. Okay, and these are their hand or whatever. Let's just say this is their hand. I don't know what kind of diagram is this, but the point is, what happens when this child is going to curl inside the tire? Now, on average, will the mass of the tire get closer to the axis of rotation? You see? Yes. So can I say it is almost like changing the tire shape from a ring shape, let's say, to something like a coin, like a disc. And the moment of inertia for a coin or a disc, it is going to be 1/2 times mass times radius squared in here. So you can see that the moment of inertia is 1, right? Here it is going to be, we could just say it is going to be half of this. You might say, well, mister, if the child is going to curl up inside the tire, the mass would increase. It is true, 100%. But look, which one of them has a bigger effect, let's say? The effect of mass getting closer to the axis of rotation or just increasing the mass? That'll be mass getting closer to the axis of rotation. In other words, you can say, it is true that the mass of the tire increased, but because the mass on average got closer to the center, to the axis of rotation, so as a result of this, now the moment of inertia got lowered or decreased. And we know that if moment of inertia decreases, then what do you think? How do you think the tire is going to roll now? Of course, it is going to roll faster. That'll be the difference between this and this. So which child is correct? Clearly the first child, the one who said that if a child curls up inside a tire, the tire is going to roll faster. That one is correct. Once again, why is that? Because when the child curls inside the tire, now on average, the mass is closer to the axis of rotation, so the moment of inertia decreases, which makes the tire to roll faster. All right, that was a good question. Now, there is a designer who was trying to or attempting to do the same thing. A bicycle designer recently modifies a bicycle by adding, let's say, cylindrical weights to the spokes of the wheel. He reasoned that this would make the mass of the wheel, on average, to be closer to the axle, in turn making the moment of inertia to be less, which allows the wheel to rotate easier, let's say. But where did he go wrong? So the question itself tells you that the designer did something wrong. What did he do wrong? All right, once again, let's just see what did he do first of all. Okay, so that is what he did. Here's, let's say, the bicycle wheel. Let's bring a bicycle wheel again. Bring a shape. Here's, let's say, a bicycle wheel. Let's just draw one more. See if we can move one of them. We'll just use this if it doesn't work. All right, let's say this is the bicycle wheel. You can see that most of the mass, or the mass, is distributed at the edge. and this is the axis of rotation. These are called the spokes of a bicycle wheel. And of course, you can have more. So what did our friend or the designer do to the bicycle wheel? He added some cylindrical weights to the spokes of the bicycle. That is what he did. These cylindrical weights he added to the spokes. He said that if I do this, the mass on average get closer to the axis of rotation, which allows the bicycle wheel to rotate easier, which means in a race, the person who's riding the bicycle possibly can win the race because now they'll have to, with less effort, they can travel faster. But because the question tells you that where did he go wrong or what did he do wrong, so that means this idea did not work. So you don't have to worry about this. Now you just have to give the reason why. Now if you notice this one here, when this designer added these cylindrical weights to the spokes of a bicycle, did he on average make the mass of a wheel, for example, did he made it any closer to the axis of rotation? You could say no, because the mass on average, like you can see that, the mass of the tire is still, like very far from the axis of rotation. If he made it something like a disc, then of course he covered the center of a tire. Then on average, of course, the mass of the tire would be closer on average to the axis of rotation. If he made or turned the wheel from something like this into a disc, into something, like that is completely covered, but as you can see here, even though he added these masses, but the mass of a bicycle on average did not get closer to the axis of rotation. In other words, what he did was only increasing the mass of the tire. And by doing this, of course, moment of inertia for a bicycle wheel, we said it is equal to 1 times mass times the radius squared. So if you only add the mass or increase the mass, if you only increase the mass of the bicycle, then of course, moment of inertia will also be increased. Once again, what did he do wrong? We'll say he added the mass without bringing the mass on average closer to the axis of rotation. That is the whole thing you need to know regarding this one here. Okay. Now, okay, I think we'll stop perhaps right at this point, and then next time we'll continue because I don't want the session to be longer than this. Next time, inshallah, we'll continue with this and the effect of increasing or decreasing the length. This would be the end of this session. Make sure you practice this because practice is the key. Even if you didn't understand this, you can rewatch this one and hoping, of course, you'll master the concepts. Don't forget what we studied. We studied the moment of inertia. We said it is the resistance or the tendency of an object to resist a change in its rotational motion. It was measured in kilogram meter squared. The equation was moment of inertia. You could say a c, a constant times mass times the radius squared. It is a scalar quantity. That means cannot be negative, cannot be zero. Not cannot be zero, just because whenever there is a mass, there is always moment of inertia. We have moment of inertia for different shapes. Remember to memorize all this shape together. Moment of inertia also depends on the mass, depends on the shape, depends on the mass distribution as well. We also said that the further the mass from the axis of rotation, the larger the moment of inertia, which means the object now, it is very difficult to rotate the object or there will be more resistance. In that case, there will be less angular speed. So based on that, we can say moment of inertia and angular speed are inversely proportional to one another. Keep practicing. I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.